Hello everyone. Today we are going to analyze this cantilever beam. In this beam, there is uniformly distributed load acting from the fixed end A for a distance of A up to the point C. From C to B, there is no load. By applying this rule, we can find RA. RA is acting upwards, so it will be positive. The UDL is acting downwards, it will be negative. For the UDL, to get the total load, we have to multiply the load with the distance W into A, it will be WA. For RA, we will get WA. To find MA from the point B, let us take a moment about A. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. The UDL W is acting in the clockwise direction, so it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. The moment MA will be acting in the anti-clockwise direction, so it will be positive. Finally, for MA, we will get WA square upon 2. Now I am going to find the shear force values from the point A and towards the point B. In this case, I have to follow right hand side rule. Upwards will be positive and downwards will be negative. At just left of A, there is nothing. So the shear force at just left of A will be 0. At just right of A, we have the vertical reaction WA. It is acting upwards, so it will be positive. Let us find the shear force in the point C. Up to the point C, we have WA and the UDL. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance A. W into A, it will be WA. For the shear force at C, we will get 0. From the point C to the point B, there is no load, so the shear force will be 0. Here you can see the shear force diagram. To find the moment at A, we can use the right hand side rule. In the point A, we have MA. It is acting in the anti-clockwise direction, so it will be negative. We know that in the free end B, the moment will be 0. From B to the point C, there is no load. In this case, the moment at C also will be 0. Here you can see the bending moment diagram. The shape of the diagram will be a second degree parabola. Using this diagram, we can find the slope and deflection in the points C and B. We can use the moment area method. Using this formula, we can find the slope. First, let us find the slope at C. The area formula of a second degree parabola is 1 by 3 into BH. Here the breadth is A, height is WA square upon 2. So this is the area. The area divided by EI, we will get the slope WA cube upon 6EI. Now let us find the slope in the point B, but up to the point B, the area is same. In this case, the slope at B and C will be same, which is WA cube upon 6EI. The formula to find the deflection is area x bar upon EI. Let us find the deflection in the point C. The area we know, only we have to find x bar. X bar is the horizontal distance from the center of gravity to the point C, that is 3 upon 4 into breadth. Here the breadth is A, so 3 upon 4 into A, we have to multiply that. In this way, for the deflection at C, we will get WA power 4 upon 8 EI. Now we are going to find the deflection at B. The area is the same, only x bar will be different. We have to find the distance up to the point B, so we have to add this distance. This distance is L minus A. For these two terms, we can take LCM. We have to multiply this and this with 4. In this way, for the deflection at B, we will get this expression. Alternatively, using MACAULAY'S method, we can find the slope and deflection at any point of the beam. To make the process a little simple, we can extend the UDL up to the point B. Also, from the point C to the point B, we have to apply uniformly distributed load in the upward direction. We have to make sections. There are two different parts, AC and CB. So we have to make two sections, one in AC and one in CB. I have made both of the sections at a distance of x from the point A. Let us find the moment in the sections. From the point A, we are going to find the moments. In this case, we have to follow right-hand side rule. Clockwise will be positive and anti-clockwise will be negative. The moment MA is acting in the anti-clockwise direction, so it will be negative. The reaction RA is acting in the clockwise direction, so it will be positive, and the distance is x. The UDL is acting in the anti-clockwise direction, so it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. So x into x by 2, we will get minus wx square upon 2. This UDL is acting in the clockwise direction, so it will be positive. For this UDL, we have to take this distance. This distance will be x minus a. We know that with the UDL, we have to multiply the distance and then the distance by 2. So it will be x minus a the whole square. These two terms should be separated by this line. We can equate the moment to ei d square y upon dx square. We have to integrate on both of the sides. When we integrate d square y upon dx square, it will be dy upon dx. Using this formula, we can integrate these three terms, and using this formula, we can integrate these. In this term, there is no x, so the integration will be x. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. When we integrate this, we will get x minus 3 the whole power cube upon 3. C1 is the constant. 2 into 3, it will be 6. One more time, we have to integrate on both of the sides. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. When we integrate x cube, it will be x power 4 upon 4. In this term, there is no x, so we have to multiply with x. C2 is the new constant. When we integrate x minus a the whole power cube, we will get x minus a the whole power 4 upon 4. 2 into 2, 4. 2 into 3, 6. 6 into 4, it will be 24. In the point A, there is a fixed support. In the fixed support, the slope will be 0. dy upon dx is the slope. We know that from the sections we have made, at A, x will be 0. In this equation, for x and dy upon dx, we have to apply 0. When we do that, we should not consider this. In this way, for C1, we will get 0. Also, in the fixed support, the deflection y will be 0. So, in this equation, now we can apply 0 for x and y. When we do that, we should not consider this. In this way, for C2, we will get 0. In these two equations, we can apply the values of C1 and C2 so that we will get these two equations. First, let us take the slope equation. For x less than a, we should not consider this. We have to only take these three terms. We can take EA on the other side. We can take W outside. Here we can take LCM. We can keep 6 as the LCM. When x is less than a, to find the slope, we can use this equation. Let us keep this equation as number 1. When x is greater than a, we have to take this term also. For these four terms, we can take LCM. Using a minus b the whole cube formula, we can expand this like this. We can eliminate x cube. We can eliminate these two, and we can eliminate these two. Finally, we will get this. Here you can see that there is no x value. That means from the point B to the point C, the slope will be constant. So in the points B and C, the slope will be same, which is minus WA cube upon 6EI. Let us keep this as the equation number 2. So using these two equations, we can find the slope at any point of the beam. Now let us take the deflection equation. For x less than a, we should not consider this. We have to only take these three terms. For these three terms, we can take LCM. Let us keep 24 as the LCM. This is the equation to find the deflection when x is less than a. Let us keep this equation as number 3. For x greater than a, we have to consider this also. For these four terms, we can keep 24 as the LCM. Using this formula, we can expand this like this. We can eliminate these two. We can eliminate these two and these two. Finally, we will get this equation. Let us keep this equation as number 4. So using these two equations, we can find the deflection at any point of the beam. To find the deflection in the point C, in any one of these equations, instead of x, we have to apply a. When we do that, we will get minus WA power 4 upon 8 EI. To find the deflection in the point B, in this equation, instead of x, we have to apply L. Finally, we will get this expression. Here you can see the elastic curve. In this table, I have summarized of what we have done. Now we are going to end this session. Thank you for watching this video.